So I'm going to continue about the topic modeling classification hierarchy. Yesterday we already learned there are some algorithm. The first is the algorithm related to non-probabilistic method. So we'll take a look on the LSA, latent semantic analysis, and non-negative matrix factorization. And for the probabilistic algorithm, it is about the probabilistic LSA or PLSA and LDA. So let's see if the time is okay. I will explain this one, but if the time is not enough, maybe this is just for your future study. Now let's go into the detail on the latent semantic analysis. LSA, or people say it is the latent semantic analysis. It is a method of topic modeling based on the singular value decomposition, or we can say it is SVD. It is a very popular approach in the linear algebra. So if you learn the linear algebra, you will learn about the SVD. In some literatures, they mention about matrix decomposition. The idea is to reduce the dimensionality. It means the attribute. As we know, when you deal with words, there will be a lot of words in one document. In order to fit with the algorithm, in order to do the calculation, we need to reduce the dimension. And the matrix decomposition is one of the idea. So we want to reduce the dimensionality of the document term matrix. Yeah. So if we do document term, it means we have document on the row, term on the column. Okay. So we want to find the latent topics. Latent means something it is hidden. So we do not know. In order to do this one, first we construct the term document matrix. So as I mentioned to you, term, if it comes first, then it is the row. Okay, so this is the term. And document. So the document will be the column. So we have the term document matrix or TDM. Its row represent a term and its column represent a document. So this matrix shows how frequently its word appears in its document. Okay, so we have A. Okay. So this is the matrix from the term document. So we have the matrix A. And we would like to decompose. Okay. Decompose. So it means we want to split into 3. So we have the U, we have sigma, and we have VT. Okay. VT is V transpose. So T means the transpose. The idea is something like this one. We have the document, we have the terms. So we want to find something in between document and terms. So there might be some numbers or there might be some hidden things in between those two in the matrix. And yeah, we are going to use the matrix decomposition to find it. So how we can find this one? So we will define U. So U is the matrix about the document and the topic relationship. So we have the document and the particular topic. Sigma. Sigma is the diagonal matrix with singular values representing the strength of its topic. So if you learn the matrix, we have a diagonal matrix. Diagonal. This is diagonal. So the value will be only in this section. It means that we can see the importance of the topic. So if there are two topics, then there will be only two values. If there are 5 topics, then there will be 5 values, and so on. And then V transpose. It is the matrix of term topic relationship. So V is the term and the topic relationship. In order to fit with the multiplication, when you do the multiplication matrix, we have the M multiplied by N matrix. Let's say this is matrix A. And then if you have matrix P, then in order to do the multiplication, you need to have the same structure. Okay. So if it is row and column of matrix A, when you do the multiplication with matrix P, so the matrix P should have the row which have the same number of column from the previous matrix. Then we will get C is the M multiplied by K. So that's the idea about this matrix decomposition. So we want to find what is the importance of the topics. Now, let's look at this simple example. I have document 1, document 2, document 3, document 4, document 5. And the document 1 is this one. I love watching basketball games. Basketball is a great sport. Document 3 mentioned the election will be held soon. Document 4, the new basketball player was elected as the MVP. Document 5, many people voted in the election. This kind of document, we can do pre-process. Okay, so you already know. Yeah, I think you are doing your assignment now. When we have this kind of text, we will do the pre-processing. The pre-processing means we can tokenize. So we check each of the word, okay, and then removing the stop words. So let's say the stop words is okay, so we remove it. And lemmatize. So lemmatize means we want to check the basic form. Maybe watching. Yeah, this might be lemmatized into watch. Okay. Voted. Okay. This might be lemmatized into vote, something like this. Okay. So this kind of documents, after we do the pre-processing, let's suppose after pre-processing, the corpus is represented as like this one. Okay, just make it like this one, just simple. Yeah, I just keep the watching like this one, and then the voted I keep like this one. So we just remove the stop words for this pre-processed data. Now, what you can do for this LSA, first you need to make the term document matrix. you already learned about the term document matrix. The term is the row and the document is the column. We have 16 terms: basketball, love, watching, games, and so on. And 5 documents, so we have 5 columns. If you look at this matrix, you can generate the TF idea. Okay. Do you still remember TF idea? So you can make the feature using the TF idea. But for this example, let me just make it simple. For simplicity, let's use the raw frequency. So it means in the basketball, there is 1 in the document 1. There is 1 term in the document 2. There is 1 term in document 4. Okay. With the singular value decomposition, we can generate the U, we can generate the sigma, and we can generate the V transpose. Okay. So U means the term topic matrix. So I'm not sure how many topics that we can generate this one. So this metric represents how terms are distributed across the topics. So we have 1, 2, 3, 4, 5. We have term and topic matrix. So it means now we want to look at 5 topics. So we have 5 documents. So it means every document represents 1 topic. We can reduce this one into maybe 3 topics. We can reduce this one into 2 topics. So you can decide how many topics do you want, and the singular value decomposition can be generated. So how to generate this one? Yeah, this is using the linear algebra. It is not our part. So I will show you later with the Python. After we have the U, so the singular value decomposition will also generate the sigma, singular value. See, this diagonal matrix capture the importance of its topic or its dimension. So the singular value will be this one. So 2.49, 2.15, 1.86, 1.54, and 1.52. So this is a diagonal matrix actually. So 2.49 and then 2.15, 1.86, 1.54, and 1.52. So this is in the diagonal. I will just make it representation like this sigma in order to make it easy. And then the VET is the document topic matrix. So the document topic matrix means we have document and then we want to check with the respective topic, because in this case we have 5 topics. So in this column we also have 5 topics. This represents the importance of each topic. When we have the document topic matrix, as you might know, if this is the topic and if this one represents the importance of the topic, then the document topic matrix should be transpose. Do you know transpose? Yeah, I hope that you already learned from the linear algebra. We have the matrix transpose. Let's say we have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. So the transpose is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we want to transform into the first one is row and column, and when we transpose, it becomes column and row. Okay. So the document and matrix, it is at the first time is 5 multiplied by 5, but when we transpose, it becomes again 5 multiplied by 5, but the topic becomes the row and the document become the column. Then we can do the multiplication. This multiply by this, multiply by this, and it should be the same with the original matrix that you have in the term document matrix. So this is the A, and then the A matrix can be decomposed into U, which is this matrix, multiplied by the sigma, the singular value, multiplied by the V transpose. Okay, so this is the singular value decomposition. It's complicated to create the SVD with n. So let me just get the number using the Python. And let's do the interpretation. Yeah, maybe in the exam, I will not ask you to do the calculation, but I will ask you to do the interpretation. So what does it mean by this SVD result? Okay, let's take a look. We have the term, okay, and we have the topic. So the topic, yeah, we can distinguish into two topics. For example, this we have topic 1 and topic 2. So the topic 1, if you look at the numbers, okay, the numbers is likely in this high number related to sports. Why? Let's see. The terms like basketball, games, player, MVP, yeah, it's just more dominant compared to the topic 2 with related to this word. Okay. Although some of the word like this one elected, maybe this is related to the other things, not about sports, but somehow, yeah, this term, this term, this term, and this term, which is more about sports, are dominant. And the topic 2, we can also look at the numbers. So 0.6, 0.2, 0.3, 0.3, this one and this one. Okay. If you look at those numbers, it seems the number like election, how many people soon voted. Okay. So for soon is not that easy to interpret, but vote, election, it is high, then it is more likely related to politics. Okay. So using this number, we can do some analysis. We cannot say for 100% sure, but we would like to say it is likely to be in sports. It is likely to be in politics. So this LSA has some limitation. when we look the topics, some of them can be negative. So this is still easy for you to interpret because of all of the numbers are positive. But when the numbers become negative, yeah, it is difficult to understand what does it mean. And LSA has problems to cope with word ambiguities. Still, yeah, some words ambiguities, we cannot solve it with the singular value decomposition because maybe it is related with the more on the pre-processing step, okay? Because this is based on the matrix. So as soon as you generate this one, of course, the SVD calculation cannot understand what is the difference between elected and election, although maybe they are similar. Okay. So let's look at the Google Colab. So in the Google Colab, I use the count factorizer to check the frequency. And then I'm also using the truncated SVD. It is for the SVD generation. The document is this one. I love watching basketball games, basketball great sport, election held soon, and this one. So it is already pre-processed. Okay. At first, let's do the frequency calculation. So we count the factor and then put into the document term matrix. And then let's apply the simple SVD. So in this case, I'm using the LSA algorithm. And when we apply the authenticated SVD, so we need to determine how many topics do you want to get. Let's say I'm going to get 2 topics. So the term topic matrix we can get from the components. The terms itself, it is based on the vocabulary, and we can get also the term topic matrix based on the terms. So this is the SVD result. Okay. When we have the we have the U, we have the V, and we have the Z. So after this one, yeah, we will check what is the importance from every this one. Actually, we need to do some kind of repetition in order to get the SVD. And then after we have the sigma, so we can set up what is the importance of the topic. So this is the final states after we do the calculation. So LSA actually is also another simple approach, but it was a very old method. And as I mentioned to you, because the LSA can give you negative value, and the negative is not easy to interpret. So there is another algorithm, not that new. So it is an old algorithm. They call it non-negative matrix factorization. So they try to handle the negative by using this matrix factorization. So the non-negative matrix factorization, or we call it NNMF, it is a dimensionality reduction technique. used in the topic modeling and other machine learning tests. So if you learn the data mining or machine learning, you can use this non-negative matrix factorization for clustering or for dimensionality reduction. So it decomposes the non-negative matrix. We have V. Okay. So we will take a look what is V into two non-negative matrices. So we have letter W and X. So we have V. We will decompose into W multiplied by X. So V is the document term matrix. Its row is the document and its column is the term or the word. W is document topic matrix. So W is document topic matrix. The row is document and column is the topic. And X is the topic term matrix. So its row is the topic and its column is the word. Okay. So let's say if we have 5 documents and we have 16 terms and we have 2 topics, then we can generate the matrix W. It is 5 multiplied by 2. We have 5 documents and 2 topics, and then we will have the H. It is the topic term matrix, so it will be 2 multiplied by 16, and we will have the matrix V, which is the document term matrix 5 multiplied by 16. Okay. So based on this idea, we want to look at the details. So the document term matrix, as I mentioned to you, the document becomes first, then it is the row, and the term means the column. So in the matrix, each row represents a document and its column represents a unique word from all the documents. So this is the same with the previous matrix, but now we transpose it. Sometimes we call this document term matrix as the pack of words. So you already learned from the previous section about pack of words. So the matrix size is 5 multiplied by 16, 5 documents and 16 words. So the NNMF, sorry, why is double? Okay, let me just use X in this case. Okay. Previously I mentioned V, but let me just use X. So we want to decompose the X into 2 matrices. So the matrix W, it is the document topic matrix, represent the distribution of topics across documents. And then H is the topic term matrix. It is to represent the distribution of words across the topics. So as I mentioned to you, we can decompose into W and H. So in this case, if we define K as the topic, let's say K equals to 2, then we have W is 5 multiplied by K, and H is K multiplied by 16. So K is the number of topics. Let's say if K equals to 2, then we can just replace this with 2. So the X is the document term matrix, which is the original matrix from the pack of words. Now, at the first time, when we do the NNMF, we will randomly initialize the matrix. So the first, we will just select any values for W and X. And the number should be non-negative values. Non-negative. It means it's positive. But why we use the word non-negative? In the mathematics, usually we call the positive value is higher than 0. If it is higher than 0, yeah, for example, 0.1. So this is positive number. Okay. But in the mathematics, 0 is not included in the positive. That's why they mention non-negative. When we call non-negative, it means we can include 0 into the numbers. So in this document topic matrix, when we generate the W and when we generate the H, there is a possibility we can generate 0. Now, for the simplicity, okay, we will have the W and we will have H. It is initialized randomly. So the document 1, document 2, document 3, document 4, document 5, topic 1 and topic 2. So let's assume that K equals 2. And then we have the H, it is the term. And then this is the topic. Okay. So those number, yeah, it is randomly initialized. So this number randomly initialized. After we do the initialization, we will do the multiplication. Okay. So the multiplication of the W and H, okay, we will do the multiplicative update rules. So the W will be multiplied with H, and then we will do the updating until this multiplication equals to the matrix V. Before I mentioned X. So until it is equivalent to the matrix X. So ensuring the non-negative values are maintained. Updating rule, of course, yeah, this is a multiplicative. And how many times of this one? Yeah, it depends on the size of the matrix. So this is the updating rule. When we do the when we want to check the new matrix, okay, the new matrix can be used with the multiplicative update rules. So I will not discuss in detail for this mathematical, but let's just think that this is the kind of repetition to find what is the best value for W and H. Okay. So after we do the updating, there might be a kind of convergence. Okay. Convergence means maybe the first matrix is totally diverse. And then once when you do the multiplication at the first time, the number is not equivalent to X. But after several repetition, after several iteration, then the number will be closely to X. And then, okay, after it is closely to X, so we can interpret the result. So for example, the matrix H might tell us that something like this one. So for example, the topic 1 has high value on this basketball games player, and then the topic 2 has the numbers for election for it and people. So we can do some interpretation. And the interpretation can be about the document topic matrix. So this is, if it is about its metric is the term topic. Then we can check what is the most important term related to the topic. And it is only a non-negative value. The document topic matrix, it means we have the document and topic. So we can look at the document which is closely to a particular topic. Okay. So this is just for example, maybe doc 1 is more about the topic 1, maybe it is related to sport, and the documentary is more likely to be the topic 2, politics. So at the end, usually we can get a kind of matrix like the W and H like this one, and we can do the interpretation. Now let's see, this is the final matrices. So using this final matrix, okay, we can see that the document 1 with the topic 1 is 0.9. The topic 2 is 0.1. The document 2 it is 0.8 on the topic 1 and 0.2 in the topic 2 and so on. So then we can say that the document 1, document 2, document 4 is most likely in the topic 1. The document 3 and the document 5 is most likely in the topic 2. Okay. So this method is more interpretable compared to the LSA. So compared to the LSA, it is more interpretable. For the H, because it is non-negative, so we can easily say that, okay, the basketball, the word basketball is more on the topic 1. The word love is more in the topic 1, but it is ambiguous, okay? Because love can be in the topic 1, in the topic 2, but here maybe because most of the document related to topic 1 use the word love. That's why it becomes higher on the topic 1. Particular words like games, it is high. Particular word like election, it is high on the topic 2, like this one. Then we can say something that the topic 2 is more likely about the politics, because the word related to politics is high on the topic 2. But the other word like many, soon, new, it is ambiguous. What is incorrect? Emerda. Right. So you cannot interpret with this kind of word. And the other thing that we need to know about this kind of result, the value in each row show the proportion or the width of each topic in that particular document. So this is width. We call it width. It is not probability. 가중치. If the width is high here, then it is most likely the document 1 in the topic 1. A higher value for a topic in the document means that the topic is more relevant or dominates the content of the document. Unlike probabilities. So this is not probability. So the value in each row do not necessarily sum to 1. So maybe you will see this one. why the result is 1.1, the summation. Yeah, actually this is not probability. This is only weight. And the weight can be more than 1. But it for sure is the high value is more relevant or dominates the content of that document to be in the topic. So the value in this row do not necessarily sum to 1, but they indicate the relative contribution of each topic to the document. So yeah, I give the example. Topic 1 contributes 0.9 and topic 2 contributes 0.1. Oh. In this case 0.2. Okay. So topic 1 is much more prominent in document 1, suggesting that it is the main topic of this document. So sometimes you can see like this one, and you don't need to worry about this. For the term topic matrix, okay, it's also the same. The value in each column of its do not represent probabilities, so their total can exceed 1. Or sometimes this total can be lower than 1. Okay, like the basketball is 0.8 and 0.1. The higher value, it means the particular topic is more important with that term. And the magnitude of the value shows the relative importance of the word within its topic. The magnitude of the values, it means if you look at some word like this one, new, okay, 0.4 and 0.6. So actually, those are a little bit confusing. Okay. Whether it is more on the topic 1 or it is more on the topic 2. But the magnitude like this one, 0.8 and 0.1. So it is highly different. So the difference is 0.7 between the two. So we can see that it is more dominant. So this is more important. Yeah, in this case, the basketball and games have high values, 0.8, 0.8 in topic 1. So we can suggest, this is just suggestion or recommendation. It is not a kind of conclusion, but based on this value, we can suggest that they are the central of this topic. The election and vote, they have a high value, 0.9, 0.7, then it is also likely to be the important keywords for that topic. Okay, so let's see. So in this code, I have the NNMF, and then later I will just use the LDA and then do the count factorization. So this is the document. We calculate the frequency and then make the words into the array, and then we try to get the factorizer from the X. So let's do with the NMF. So NMF is one of the library in Python. We can set up, for example, the number of component is 2. So the key is 2. Then you can generate 2 topics. And the init, it means the initial value is random. Random state 42. So when you run this code, because it is random, I hope that the result in your computer, in my computer, will be the same, because we just put this random state. So we can do the fitness into the W and the H. And then, yeah, we can just run. There will be the document term matrix, and then there will be the result from the document term matrix. We have the result from the NNMF. So you can see here, document 1, topic 1. So here it has high value compared to the topic 2. So in the topic 2, it is E minus 0.8. What is it? In Python, this kind of number means 10 multiply 10 power of minus 8. 10 power of minus 8. What does it mean? It is 1.46 divided by 10 power of 8. So minus, in this case, it is the division. Then it means this number is very small. Okay? This weight is very small. Because this weight is very small, then we can say that the document 1 is more likely in the topic 1. The document 1, document 0 means the document 1 in our case. Document 1, it means the document 2 in our example. So it is more likely in the topic 1. So here you can see 6.37 multiplied by 10 power of minus 1. So it means 0.637. And this is 0. Then, yeah, it is more likely in the topic 2 for the document index 2. The topic term matrix is also the same. Okay, we have the topic and the respective term. The topic 1 and the topic 2, the basketball, it shows 1.27. Okay, you can see here. This is a number more than 1. So it is possible to have a number more than 1. But this number is 1.27 multiplied by 10 power of minus 9. Then it is 1.27 divided by 10 power of 9. So it is very small. Then the basketball keyword is more on the topic 1 compared to the topic 2. And the remaining, yeah, is also the same. You can see the result. And yeah, we can see the topic distribution like this one. Okay, so okay, let's have a break. Okay, I will continue after break.